This is part 1 of lecture 4.3, functions. In this video, we will give the definition of a function and learn how to prove if a given relation is or is not a function. Let A and B be non-empty sets. A function from A to B is a relation from A to B such that for any element x in A, there is a unique y in B such that the ordered pair xy is an element of f. We sometimes write the function f from A to B as shown. If the ordered pair xy is an element of f, we write y as f open parentheses x close parentheses, which we read as f of x. The following Venn diagrams are examples of relations which are functions from set A to set B. Observe that in a function, it is possible for two different elements in the domain to correspond to the same element in the range. In contrast, here are some Venn diagrams of relations which are not functions from the set A to the set B. In the relation on the left, there is an element in the set A which does not correspond to any element in the set B. Hence, the relation is not a function from A to B. In the relation on the right, some element of set A corresponds to more than one element in set B. So again, the relation is not a function from set A to set B. For a function f from set A to set B, the set B is called a codomain of f. If the object x is related to the object y under f, y is called the image of x. On the other hand, x is called a pre-image of y. Note that by the definition of a function, the image of any object in the domain is unique, but the pre-image of an object in the range is not necessarily unique. Consider the relation f consisting of all ordered pairs xy of real numbers satisfying the equation x plus y equals x times y. We claim that this is a function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. This is equivalent to the condition for any element x in the set of all real numbers not equal to 1, there is a unique element y in the set of all real numbers not equal to 1 such that x plus y equals x times y. We begin our proof by letting x be any real number not equal to 1. To prove existence, take y to be x over x minus 1. We need to show that y is a real number not equal to 1 and that x plus y equals x times y. Since x is not equal to 1, the denominator x minus 1 is non-zero, so y is a real number. To show that y is not equal to 1, observe that if y equals 1, then x over x minus 1 equals 1, so x equals x minus 1, and thus 0 equals minus 1, a contradiction. Hence, y is not equal to 1, and y is an element of the set of all real numbers not equal to 1. Moreover, x plus y is equal to x plus x over x minus 1, which is equal to x squared minus x plus x all over x minus 1, which is equal to x squared over x minus 1, which is equal to x times x over x minus 1, which is equal to x times y. Thus, the ordered pair xy is an element of f. This proves existence. To prove uniqueness, let y and z be real numbers not equal to 1. Assume that the ordered pairs xy and xz are elements of f. Then x plus y equals x times y, and x plus z equals x times z. So xy minus y equals xz minus z. Therefore, x minus 1 times y equals x minus 1 times z. Since x is not equal to 1, x minus 1 is non-zero, and the cancellation law for multiplication applies. Thus, y equals z. This proves uniqueness. Therefore, f is a function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. Consider the relation G consisting of all ordered pairs xy of real numbers such that x squared plus y squared equals 1. We claim that G is not a function from the closed interval from -1 to 1 to the closed interval from -1 to 1. That is, it is not the case that for any number x in the closed interval from -1 to 1, there is a unique number y in the closed interval from -1 to 1, such that x squared plus y squared equals 1. This is equivalent to the condition that for some number x in the closed interval from -1 to 1, either there is no number y in the closed interval from -1 to 1, such that x squared plus y squared equals y, or there are numbers y and z in the closed interval from -1 to 1, such that x squared plus y squared equals 1, and x squared plus z squared equals 1, and y is not equal to z. Indeed, take x to be 0, y to be 1, and z to be -1. Then, both y and z are numbers in the closed interval from -1 to 1, with x squared plus y squared equals 1, and x squared plus z squared equals 1. However, y is not equal to z. So g is not a function from the closed interval from -1 to 1 to the closed interval from -1 to 1. Next, we will show that two functions f and g are equal if and only if they have equal domain and the same image for every object in their domain. Assume first that f and g are equal. We will show that the domain of f is equal to the domain of g. Let x be an object. X is an element of the domain of f if and only if, for some object y, the ordered pair xy is an element of f. Since f is equal to g, xy is an element of f if and only if xy is an element of g. So the above is equivalent to the statement, for some object x, the ordered pair xy is an element of g. This in turn is equivalent to the condition that x is an element of the domain of g. Therefore, the domain of f is indeed equal to the domain of g. Next, we show that for any object x in the domain of f, f of x equals g of x. Let x be an element of the domain of f. Then there is an object y such that the ordered pair xy is an element of f. Since f equals g, it follows that xy is an element of g. So y equals f of x and y equals g of x. Therefore, f of x is indeed equal to g of x. For the converse, assume that the domain of f is equal to the domain of g, and that f of x equals g of x for any object x in the domain of f. We will show that f equals g. Let x and y be objects. The ordered pair xy is an element of f if and only if x is an element of the domain of f and y equals f of x. Since the domain of f is equal to the domain of g, the condition x is an element of the domain of f is equivalent to the condition x is an element of the domain of g. Since f of x equals g of x, the condition y equals f of x is equivalent to the condition y equals g of x. So the above is equivalent to x is an element of the domain of G and y equals g of x. This holds if and only if the ordered pair xy is an element of G. Therefore, f is equal to G. You have come to the end of part 1 of lecture 4.3. You may now proceed to part 2. Thank you for your attention.